Okay, second lecture, cycles and Euler cycles in graphs. So in this lecture, we define cycles and Euler cycles. Euler being a mathematician from the 1800s, no, 1700s mathematician, and we'll present a theorem and some examples. So in a graph, we have some definitions. A cycle is a path that has no repeated edges, so you don't go over any edge twice, and it starts and ends at the same vertex. A simple cycle is one that doesn't repeat any vertices, and an Euler cycle is a cycle that goes through all the edges. So then note that Euler cycles are generally not simple cycles, because if you're going to go through all the edges, you're probably going to have to repeat a vertex. No cycle, though, right? Keep in mind that the definition of the cycle means that you do not repeat an edge. You never repeat an edge in any cycle that you deal with. So what's a simple cycle? This is a basic example. A simple cycle of length 4 in the graph below that starts and ends at vertex B. So if we start at B, a simple cycle of length 4 means that we'll go through, there'll be a cycle that has 4 vertices, right? So B to D, 1, 2, 3, 4. So B to D to E to C, and then back to B is a simple cycle of length 4 because there's 4 distinct vertices, 1, 2, 3, 4, or 4 distinct edges. And it starts and ends at vertex B. You don't go through any edges twice, and you don't, since it's a simple cycle, you don't repeat any vertex. So that's basically about basically what cycles are. Okay, so an Euler cycle, here's our graph. What's an Euler cycle? An Euler cycle goes through all edges, but never repeats an edge. So can we find an Euler cycle for this? And this is sort of a very typical way that a lot of stuff in graph theory works is, to see whether or not there's an Euler cycle, start at some point and work your way around the graph and see if you can do it. So let's suppose we'll start at C, right? We need to go through every edge. So suppose we say, well, we have to go from C to somewhere. So we'll go from C to E. And then we have to cover this edge. So we'll go from E to D. And then, well, we have to cover this edge. So we can go back to C. In an Euler cycle, you can repeat vertices, right? And so we're going to have to repeat C. In fact, if we can have an Euler cycle, we're going to have to go in and out of C a couple of times because there's 3 vertices there. And then from C, we can go back down to B. If we think about it a little bit, we have a problem. A cycle starts and ends at the same vertex, but we can't get back to C. Right? We've used all the edges going in and out of C already. So we can't have an Euler cycle. And so you can see this, there's a problem there, right? Is that, regardless of how you try to build your Euler cycle, wherever you started at, you're going to have a problem at C, because if you go into C, you have to come out of C. But there's this extra line here. So if you go into C there, and you're not allowed to repeat it, if you've done these 2 already, then you can't get back to C. So here's one where we can actually find an Euler cycle. It doesn't matter where you choose to start, right? If there's an Euler cycle, you should be able to get to every vertex because you're going to cover every edge, and you have to start and end at the same place, so you can always just pick wherever you want to start. So if we start at A, where can we go? Well, if we go A to C, A to C, and then C to G, G to J, and then we can go back up from J up to C, and then back out of C. And now we're good, right? Because we've gone through C, we've covered everything coming in and out of C. We've covered everything in coming out of G, right? We still have to do, say, F to J. And now we've dealt all with J. We still have to do F. Now we're sitting at H from J. I, F, B. Let's see, how do I want to do this? If we go to E, B, F, I have to end at A is the problem, and I have to remember how to figure out how to do this. So H takes us to I. Right, H goes to I. We can go F, B, and then B down to I up to E up to B out to A down to E down to H, and then finally H to D, and then that takes us back to A. And so that's a whole Euler cycle. I went through each edge exactly once. Had to go through a bunch of the vertices a number of times. But notice that you have to go in and out of every vertex, right? And that always takes two. Going in and out takes one vertex in and one vertex out. Going in and out takes one vertex in and one vertex out. Degree 2 vertices are particularly, I don't know, they're features that are kind of important because there's only one way, there's only one path through them. Like A, you can go in and out a couple of different ways, but D, you're going from H to A or A to H, right? That's the only options. And we'll see degree 2 vertices again. Why does this graph have no Euler cycle? It's not connected, right? You can't get from G to C or F or E, right? It's in two parts. And those two parts are called components, right? So if you have a graph that's in different pieces, you have different components. Think of the digraphs that we did for equivalence relations. Those all had different components. So here's our theorem. How do you tell if a graph has an Euler cycle? It has to be connected, right? You can't have two different pieces like that. And every vertex has to have an even degree, right? You have to be able to go in and out of that. So this one definitely, every vertex, degree 4, degree 4, degree 4, degree 2, degree 4, you can tell that that has an Euler cycle. This one, C, that's degree 3, right? Which means you can't go in and out of it and have an Euler cycle through there. Okay.